All right, guys, we're going to move into chapter 5 here. It's one of my favorite chapters. It's probability. So let's go over a term real quick. So very simply, probability is the mathematics of chance. All right. So the big idea is that chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. All right. So let's do this thinking exercise. It says, think about the following situation. Situation 1, tossing a coin 5 times and getting 4 or more heads, and tossing a coin 50 times and getting 40 or more heads. Which situation is more likely to occur? Or do both situations have the same probability of occurring? And take into account this idea of chance behavior. Okay? So it's unpredictable in the short run. If I only toss a coin 5 times, that's a small number of trials. Okay? Now, would we expect to get 4 or more heads? Well, out of 5, since the chance of getting a head is 50%, if I toss a coin 5 times, I would expect about 2.5. Okay? I would expect about 2.5 heads. All right? 4 isn't that far away from 2.5. Okay? Now, if I toss a coin 50 times, I would expect about 25, because 25 is half of 50. Okay. Notice 40 is a lot further away from 25 than 4 is away from 2.5. Okay, it's a lot further away. So which situation is more likely to occur? Situation 1 is more likely to occur. Because 4 is closer to 2.5 than 40 is to 25. And I'm just going to actually tell you what the probability that we would observe that is, theoretically. Okay, situation 1, that would actually happen. There's a 18.75% chance that situation 1 would occur. All right. But there's only, for situation 2, there's only a 0.0012% chance that situation 2 would occur. And later we'll figure out how to actually calculate those probabilities, but those are the probabilities. Okay. You might have thought, well, it's 80%. 4 is 80% of 5, and 40 is 80% of 50. All right, that doesn't really matter. Over the long run, okay, if we toss a coin many times, we expect it to come up heads about 50%. All right, the further we get away from that, the less likely it is to occur. All right, 2.5 is much closer to 4 than 25 is to 40. And that illustrates the law of large numbers. And what the law of large numbers says, as we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value, which we call the probability of that outcome. All right. As we toss a fair coin over and over, the proportion of times that it will land on heads will approach 0.5 or 50%. When we toss a coin 1,000 times, we would expect the number of times a coin comes up heads to be about 500, because 500 is 50% of 1,000. Now, is it going to be exactly 500? Probably not, but it should be fairly close. The chances that it is far away from 500 is really low. All right. So basically, like if I made a graph and On this, I put coin flips. If I only toss a coin once, all right, if it comes up heads, I'm at 100% probability. Okay, so if we put probability on this axis, the highest it can go is 100% or 1. Okay? So if it comes up heads, then I'm at 100%, not anywhere close to 50%. But let's say the next one comes up tails. So I have one head and one tail. So my cumulative probability is dropped to 50%. All right, and this kind of deviates along the way, but as we add more and more flips, as we go out towards infinity, all right, it almost looks like a straight line because this probability is going to come close to 50% the more and more flips we do. So let's talk about a few specific laws of probability. All right, the probability of any outcome always has to be a number between 0 and 1, and we can express it as a fraction, as a decimal, or a percent. So we can express this as a fraction, a decimal, or a percent. Okay. So for instance, the probability that I get one head, I can express as a fraction, as 1/2. I can express it as a decimal, 50.50, or I can express it as a percent, 50%. Right. If we know an outcome will not occur, then it's going to have a probability of 0. All right. An outcome that we know is certain to occur has a probability of 1. And the mathematics that we're going to get into, the mathematics of probability is based on imagining what would happen in an indefinitely long series of trials, kind of like this graph up here. All right. So what is simulation? Simulation is us using mathematics to imitate chance behavior, all right, based on a model that accurately reflects the situation. For example, rather than having 100 children to find an estimate for the true probability of having a girl, we could put 2 names in a hat, okay, and those names are boy and girl. All right, and we can draw and replace a card 100 times and record our results. And oftentimes we can use technologies such as a computer applet or a calculator to simulate this chance behavior. Okay, so let me kind of show you an example there. So let's say I let boy equal 1 and I let girl equal 2. All right, let's say I do that. All right, now before I start this, I'm just clearing my list in my calculator. All right, so here's what I'm going to do. All right, I'm going to say, okay, calculator. I'm going to say, I want you to pick an, all right, I'm going to go down to number 5. All right, calculator, pick a random integer, all right, between 1 and 2, including 1 and 2. And I want you to do 100 of those. All right, and I want you to paste. Now, rather than just look at the numbers, I want you to store these in list 1. I'm going to hit enter here. It gives me the number. So I have a kid and it's number 2, it's a girl. Then I have another kid, it's another girl. Then I have a boy, 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 boy. Then girl, girl, girl. Then boy, then girl, then boy. All right, and I've put this data into list 1. So if I look at list 1, there's all the data. Now we know we can sort this data. So let me go and sort this ascending. Okay, so sort ascending list 1. All right, so now let's look at it. All right, so it's going to put all the ones first. It's going to put all the boys first. I'm just going to go down and see how many boys there are. Okay. So in this simulation, the last one happens in the 47th row. So I actually, in this simulation, I got 47 boys, and that means that I would have 53 girls. because I only did it 100 times. There's 100 children. So this simulation imitates the chance behavior. Okay, it imitates the chance behavior. What would we expect? We would expect about 50-50. That's what we would expect. Yeah, that's what we would expect. All right, so it's close to that, but it's not exactly that because it's a simulation. If you had 100 kids, you probably wouldn't have exactly 50 boys and 50 girls as well. Okay. So let's look at the next exercise about simulation. Sorry here, my screen's a little bit delayed. So let's read this exercise. It says, at a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery at a school assembly. The 2 lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member from the AP Stats class. When both golden tickets went to members of that same class, being the AP Stats class, some people thought the lottery had been rigged. There are 28 students in the AP Statistics class, all of whom are eligible to park on campus. It says design and carry out a simulation with 30 trials, decide whether it's plausible that the lottery was carried out fairly using table D. Okay, so here's what we're going to do. First thing we have to do is we need to kind of make a rule. Okay, so we need to make a simulation that mirrors this situation. All right, so we're going to let students eligible to park all right. There's 95 people. All right, 95 students have permission to park. All right, so I'm going to let the numbers 0, 0 to 94, that's actually 95 values, represent the students eligible to park. All right, now I'm going to let, before I even look at the random digit table, we're going to label the students in AP Stats. How many are they? How many of them are they? All right. Well, there's 28 students in AP Stats. All right. So this is all students eligible to park. All students eligible to park. Now, we're going to, of those students that are eligible to park, 28 are in AP Stats. So the first 27, 0, 0 to 27 would represent the students in the AP class. All right. Students not in AP Stats would be comprised of the other ones. Okay, so that would be numbers 28 to 94. All right. So we're going to use table D, and let's just start at the beginning there. Okay, let's use, I'm just going to pick a row at random here. Opening up my book. All right. Let's start at line 101. Okay, let's start at line 101. All right. So here, I'm going to put trial number and student. All right, so they want me to do 30 trials. Or student selected. So trial 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So we're going to do this simulation 30 times. Okay, starting on line 101. All right, so line 101, it says my first two numbers are 19, then 22. If I keep going, I have 39 and 50. If I ever get a number bigger than 94, I'm going to ignore it because I only have 94 students. All right, so I have 39 and 50, then I have 34 and 5, then I have 75 and 62, I have 87 and 13, I have 96, but I'm going to ignore 96 because I don't have a 96 student. All right, then I have 40 and 91, 25 and 31, 42 and 54, 1, 2, 3, 4, 5, 6, 7, 8. All right, then I have 48 and 28. Then I have 53, and I have to go on to my next row. 53 and 73. 67, 64. And 71, 50. Then 99, 40. But I can't use 99 because I don't have a 99 student. Then I have 0, 0. I do have a 0, 0 student. All right. Then I have 1927. Then in the next trial, I have 2775 and 4426 and 4882, 4253, 6290. I have to go on to the next row. 45, 46, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. 77, 17. 977. 5580. 00, 95, but I have to eliminate 95 because I only can go up to 94. So I'll go 32, 86, 32, sorry, I lost my place, I gotta refund it. 86, 32, okay. 94, I do have a 94, 85, 82, 22, 69, 00, 56, to go on to the next row, 52, 71, and 13. All right. So basically, if we pick two students at random, student number 19 and student number 22 would be the two students' numbers that would get the two golden ticket. They would win the golden ticket parking lottery. So the stat students are numbered 0 to 27. So let's double 0 to 27. So I'm going to circle every time I see a number between 00 and 27. Double 0 to 27. I think I got them all. All right. So in the very first lottery, just using chance behavior of a random digit table, 2 students from AP Stats got selected. All right. Here, nobody got selected. Then 0 AP Stats students got selected. 1 AP Stats student got selected. Here, nobody did. Then 1, then 0, then 1, then 0, 0, 0. Right, then 0, 0. 1 AP Stats student got selected. Then we have 2 again. Then we have 1. Then we have 1. Then we have a whole bunch of months that go by where no AP students get selected. All right. Then we have the next month, we got 1, then 0, then 1, then 0, 0, 1, 1, 0, and 1. All right. So treat each trial like a month, okay? So you start this process in month 1, 2 students from AP Stats both got selected. They both won the lottery. Well, how many times did that happen over 30 months? Well, it happened in trial 1. All right, it happened in trial 1, and it happened in trial 14. All right, happened in 1 and in trial 14. So we could say out of 30 months, the simulation revealed that that 2 AP Stat students winning the lottery happened twice. So what's that probability based off our simulation? Well, it happened 2 times out of 30. So on my calculator, if I did 2 divided by 30, that's the same as 1 over 15. That's 6.66%. Right. Now, this is a low probability, but to me, 2 out of 30, even though the simulation revealed there's a small chance of that happening, this is still big enough, 6% to me, almost 7%, is still big enough to believe it's plausible, that it was not rigged. Okay? I still think that that's believable. If this thing was less than 5%, I wouldn't believe it as much. Okay, but if it's over 5%, it's to me it's more plausible that it could happen. It didn't say is it probable. It's not probable. Okay? It's not probable, but it is plausible based on this number right here. Okay. So let's do the same thing, but let's do it this time using our graphing calculator. Okay, so it's going to be the same thing. All right, so I'm going to have trial. Two, 3, 4, 5, 6, 7, 8, 9, 10. Student selected. All right, sorry, that pen's not, the red's not working very well. So trial, student selected, trial, student selected. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay. So here's how I'm going to do this. So let me get rid of my data that's in list 1 right now. All right. So we can do this in a number of ways. Okay. Here's probably the easiest. We can go math, go over to the probability section, and go down to number 8, random integer no repeat. So let's make it the same way. 0, we'll start at 0 and we'll go up to 97. But I'm going to pick 2 at a time. All right. I'm going to paste that. Okay, before I do that, let's seed our calculator so we all get the same thing. I'm just going to seed mine with 10. 10 math, rand, it's going to seed. All right. So math, probability. We're going to go to number 8, random integer, no repeat. 0 to 97, I'm going to pick 2 at a time. That way I don't get the same person winning both tickets. All right, so paste. All right, so it says 44.54. All right. All right, I do it. I hit enter again, then I get 24.67, 84.83, 78.21. 26.63, 90.47, 17.43, 3.97, 65.58, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5.94. 267, 79, 73, 62, 68, 32, 86, 131, 52, 80, 58, 62, 95.41, 27.8, 13.94, 63.11, 82.48, 27.95, 45.68, 52.84, 19.93, 27.35, 14.21, 13.73, 81.87. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so let's do the same thing. Okay, we just ran another simulation. We just use our graphing calculator instead. Let's circle all the numbers that are 27 and smaller. So 27 and smaller. So here I have none. No AP stats are selected. Okay, here I have 1, then I have 0, then I have 1, then I have 1, then I have 0, then I have 1, then I have 1, there's 0, and I have 1 AP Stat student selected. Okay. All right, then I have 1, then 0, then 0, then 0, then 1, then 0, then 0, then 0. Oh, here we go. We got 2 numbers that are 27 or less. We got 1. We got 1. We got 0. We got 1. We got 0. We got 0. Then I got 1. Then I got 1. We got another 2 here. Then I got 1. And then I got 0. Okay, so even if I did it on the calculator 2 times, there was twice. In the 28th trial, I got 2 AP Stat students. And in the 19th trial, I got 2 stat students. So we would expect 2 stat students to get chosen about 2 out of 30 times, which is about 6.66% or 6.67% if I round. Again, this number is small, but it's not so small as I don't believe it's not plausible. Not probable, but plausible. All right, it's not going to be a huge surprise when it does happen. So I believe that the lottery was carried out fairly. If this number was smaller than 5%, I would start to doubt it. Okay, that's kind of my threshold. If the probability of something happening is only 5%, I don't really think that it's plausible. You could even have a lower threshold than that. You could say like 1%. If the chance of something happening is 1%, you don't believe it's probable. Okay. My bar is generally 5%, and generally in statistics, 5% is what we use as a threshold. Okay. So it is plausible. It is plausible. You can't cast doubt when something's plausible, where it could happen. All right, so that's how we can do simulations. And a lot of times on the AP stats test, they'll give you graphs, okay? They'll give you like a histogram of simulations, the results of a simulation. And they're gonna ask you questions about that simulation, all right? So ask yourself, what's your bar to believe something? So we're gonna stop the video there, and that's the end of the notes for the intro to Chapter 5 and 5.1, randomness, probability, and simulation.